All right, finally, the last video from 1.6 part 2, this section where we get into some pictures to summarize data, to do descriptive statistics with plots. We've learned 3 different ways to do it so far. We've learned a histogram, which is important. We've learned a stem and leaf plot, less important. And we've learned a box plot, fairly important again. There's more ways, more pictures you can make, but in this class, those are the 3 we're going to talk about. In this video, I'm not going to introduce a new picture, a new type of plot. But in fact, I'm going to introduce a characteristic that you can get out of any of those 3, and it's this notion of shape, the shape of a distribution. So the idea here is I want a word that kind of describes what my histogram kind of sort of looks like, or what my box plot kind of sort of looks like. And that might seem like an impossible task because you could have infinitely many different histograms or box plots. But what I'm going to do is I'm going to kind of make some categories. I'm going to show you 4 different types of shapes. So sure. 4 shapes. And what I will ask you to do is make a histogram or make a box plot or a stem and leaf plot. And then after you make your histogram, box plot, stem and leaf plot, you tell me, all right, it looks the most like this type out of these 4 that I list for you. And what I'll do, since this is an intro to statistics class, is I'll kind of contrive the problem in such a way that I'll pick the data really carefully so that it looks a lot like one of these 4 types. Although in reality, sometimes it's like, it kind of looks like this type, it kind of looks like this type, kind of sort of stuck in the middle. So 4 different shapes. I'm going to first draw for you 4 different shapes, and then I'm going to explain what the hell I mean by these shapes that I'm drawing. So that will end up being my first type, I'll put it in there. My second type, I'll put it in there. My third type, I'll put it in here. And my 4th type, I'll put it in here. And what I'm going to draw for you are things that kind of sort of look like histograms, think histograms, but they're actually not histograms because they're curves. Sure, that's good enough. As opposed to these discrete boxes. Those are my 4 different types. They have 4 different names. The names that we will use in this class is this first one. We're going to call it symmetric. And when I say symmetric, I mean like if you drew a line down the middle here, there's some symmetry. The left-hand side kind of looks like a mirror image of the right-hand side. Maybe not exactly because I'm not a great artist, but maybe you can kind of see how I meant for this side to look for this, like this side. But you might have an issue there. You might be like, whoa, this one's over here symmetric as well. If I put the line right here, the left side kind of looks the same as the right side. True. So I can't just call this symmetric. I'm going to call it symmetric bell-shaped. Bell-shaped, I guess, think like Liberty Bell, like old school bells. You can kind of picture this as the outside of a bell and the little thing, I don't know what it's called, on the inside of a bell swinging back and forth. Anyway, symmetric bell-shaped is what we're going to call this. Turns out that there's a distribution that's very famous that has this shape. We haven't learned about it yet. We won't learn about it till chapter 3. But it's called the normal distribution. So the shape is symmetric bell shape, but a specific distribution that has this symmetric bell shape is a distribution called the normal distribution. And so when the class goes on, this will kind of be synonymous. Instead of saying symmetric bell shape, kind of a mouthful, we'll describe it as normal or normally distributed. But for now, since you haven't learned about the normal distribution, I'm going to call it symmetric bell shape. These 2 are not symmetric. The term that we use in statistics as opposed to symmetric is skewed. S-K-E-W-E-D. These are both skewed distributions. But they're a little bit different, right? This one looks different from this one. This one, I got most of the observations are over that. It's really high over here on the left-hand side, and then there's this kind of tail going down to the right. Whereas this one, the tail is going down to the left, and the height is over on the right-hand side. One of these is called left skewed, one of these is called right skewed. And probably the most common mistake people make in a Math 243 class, an intro to statistics class, is confusing the 2. My hint is the name for the skew is based on the tail. So I'll explain in a minute how this thing over here is called the tail. The tail's on the right side. So this thing is called right skewed. This is the tail over here. It's on the left. So this thing is called left skewed. Turns out these 3 are the 3 important shapes for this class. But there's a 4th one that shows up in the homework every once in a while, so I'm going to include it. Although really what your goal will be in this class is to distinguish between these 3 types. Left skewed, right skewed, and symmetric bell shaped, which we'll later call normal. Just for completion, this thing over here is called a uniform distribution. It's also symmetric, but usually it's not described as symmetric flat shaped or symmetric board shaped or something. It's described as uniform. Fine, that's my distribution there. Those are the 4 different types. And now you're like, whoa, I haven't made, where are these curves coming from? How is this tied into anything that I've done so far? These are supposed to look like histograms. And I know they might not immediately look like histograms, but if I go back to this histogram that we made, maybe if you stare at this histogram, you see most of the observations over here on the, if I had to draw a curve that kind of sort of approximated the heights of these bins, maybe it would kind of look like this. Right? Maybe you can kind of see, loosely speaking, a right skewed distribution here, because most of my observations are over here on the left-hand side, but I have this tail going out to the right. It's a right skewed distribution. That was what, this is an example of something that I want you to be able to characterize as a right skewed distribution. So when I say symmetric here, really the way to think about it is if I made a box plot, and the box plot kind of looked like this, or sorry, not a box plot, a histogram, and the histogram kind of sort of looked like this, right? These are the heights of all the different bins. You might be like, oh, it kind of looks like this symmetric bell shape. I can kind of sort of see that. But it'd be annoying if whenever I talked about the shape, I had to draw all these different rectangles. It's a lot easier to just draw the curve. So a histogram that would kind of look like this guy would be something where the tall bins are over here on the left-hand side. Most of the observations fall over on the left. But then I get a bunch of, not very many of them, but observations that are significantly greater than the rest of them. That's this tail idea over here. Note that I don't have any observations that, most of my data is in here. I don't have any observations that are way less than these guys. There's nothing over here. But I do have observations that are way more than these guys. That's what creates the tail. Compare that to this one, where most of the observations, the tall bins in my histogram, are over here on the right side. Right, maybe I'd have something that looks like this. And there's nothing way out to the right. It kind of stops here. Maybe you have a little one there. But out to the left, I do get these observations way out to the left. There's not very many of them. These bins aren't very tall here. But it creates this tail going out to the left, which is what gives this its left skewed name. Uniform, you got a bunch of rectangles that are more or less the same height. So maybe they're not exactly the same height, but pretty damn close to the same height. There's some kind of region on which your data lives, and anywhere on that region, all the heights are about the same. That's what's called uniform. These are the 4 different types you want to distinguish between. The first level of difficulty is I give you data, you make a histogram, you look at that histogram, you talk about which of these types it is. That's like this problem. You make a histogram, and you're like, most of the observations are over here on the left, but I have this tail going out to the right. This would be a right skewed distribution. Similarly, you can do that from a stem and leaf plot, because all a stem and leaf plot is a sideways histogram. If you turn your head 90 degrees to the right, you can kind of see a histogram here with most of the observations over on the left if your head is turned sideways, but this tail going down to the right. This would also be a right skewed distribution. Turns out the second level of difficulty is that you can get these not just out of histograms, but you can get them out of box plots. It's just a little bit more challenging. But the idea with the box plot is what this is telling me is my first quartile is here and my third quartile is here. So 3/4 of my data is over here, right? Less than my third quartile. 50% of my data falls between the first and third quartiles. Most of my data is over here between 5 and 20, give or take. If I were to make a histogram, and I'm not making a histogram, but if I were to make a histogram out of this data, I would have pretty tall bins over here, because I have lots of observations over here. Most of my observations fall over here, but not all of them. I got a few way out here, right? And then there's even one way out here and one way out here. Maybe you can kind of see from this box plot that I also have this right skewed shape. Most of the observations are on the left, but I have a tail going out to the right. I think it's a little bit harder to get shape out of a box plot. Some characteristics of skew is when the median is closer to one of your 2 quartiles. I guess that should have been Q1. If the median is closer to Q1 and this little whisker is shorter on the left side, then what that means is most of my observations are over here on the left, so therefore it's right skewed. Outliers. They don't necessarily tell you that something's skewed, but it's a lot more likely that you'll have outliers on the right if you have right skewed data. And if you have left skewed data, maybe you can kind of imagine this sort of flipped over. If I had some outliers over here, if most of my observations were over on the right, but I had a couple over here on the left, well, maybe I made a, oh, that's kind of weird looking, but fine. These should all be the same width. Maybe I had a histogram that looks like this. If I were to try to make a box plot out of this, maybe my median's here, most of my observations, but I get some way out here, and maybe this guy was an outlier. Maybe you can kind of see that a box plot that kind of sort of looks like this will correspond with the histogram that kind of sort of looks like this, which would be an example of something that is left skewed. So when the median is closer, when I have a right skewed distribution, the median is closer to Q1, and the whisker on the right is a little bit longer, and it's more likely that I'll have outliers on the right. When I have a left skewed distribution, the median is closer to my third quartile than it is to my first quartile. The whisker on the left is longer, and if I have outliers, they're most likely going to be over here on the left side. That's a left skewed distribution over there. One that's symmetric, the median is roughly in the middle between the first and third quartile. The whiskers are about the same length on both sides, and it's pretty unlikely that you have outliers at all. But if you don't expect there to be several outliers on one side of the distribution, I guess, if you're symmetric bell-shaped. So the second level of abstraction is, can you tell the different shapes, not from a histogram or even a stem and leaf plot, but from a box plot? And the third and final level of abstraction, which is the hardest one, so I don't know, take it with a grain of salt. If you can kind of sort of understand this, you're doing really good, and I'll ask these sparingly as far as tests and stuff go, is if I describe a situation to you, can you determine whether the data from that situation would likely be symmetric bell-shaped, right skewed, left skewed, or uniform? And that can be kind of hard, and that causes a lot of arguments when I give you one of these on a test and you're like, I didn't think about it that way, but maybe I can just tell you a couple of examples that I've used in the past, and I can kind of show you the logic of why I thought they fit one of these different categories. And then maybe if you see these exact same ones later on in the class, you won't be as angry when you see them on a test. An example that I think was on the most recent midterm I gave was the number of math classes that a college student takes before they graduate. The number of classes that they took, of math classes. So like, I don't know, you're a theater major and you're like, I got to take one math class. I'm not thrilled about it. I don't like math. It's not my thing, but I got to take one to satisfy my quantitative reasoning requirement. Or somebody else is like, yeah, I'm doing, I don't know, a history major. And I took a couple. Math, that's all right. I like it. I don't love it. I had to take two of them and I took one more because I found it interesting. I think most people would take, I don't know, between 1 and 5 math classes maybe. I think most observations, if I were trying to track the number of math classes that students took, would be over here. There'd certainly be some students that took either 0 or 1, and then a lot that probably took 1 or 2 or 3 or 4. Maybe it'd look like this. But then you start getting into, I don't know, some science majors, right? I'm a chem major and I have to take Calc 4, and I had to take 6 math classes to get that far, right? There's going to be people taking more. Or consider a math major, right? Maybe a math minor is taking 9 classes. A math major, they might be taking like 20 classes, right? They might be way the hell out here. If I made my histogram, most of my observations would be over here on the left, but I'd have this big long tail going out to the right. Note, I can't have a tail going to the left because you can't take a negative number of math classes. But since I'd have some students who took a lot more math classes, namely math majors or math minors or people that really like math, I'd have this big tail going out to the right. When I put this on a test, I had in mind right skewed for that example. Another thing that ended up being right skewed was the age of students at a university. The age of students at, I don't know, SOU or whatever school you want to talk about. But again, you're like, well, I don't know anything about the age of students at a university. Okay, that's fair. But most standard college students go to college after high school or maybe a year after, right? So maybe they start when they're, I don't know, 18, 19, something like that, 20. Some start a little bit later, or maybe if you're a senior, you're still going. Maybe you're super senior, you've been there 5, 6 years, whatever, that's all fine. I think most college students are between maybe 18 and 25. If I were making a histogram, right, and here's 10 and 20 and 30, 40, 50, and so on. I think most people, I mean, there'd be some in this bucket, right, because there's the 18 and the 19-year-olds. I think most would fall in here, 20 to 30. But there's some 30 to 40 for sure, right? You get somebody who, I don't know, is coming back to school after a while. Maybe it's not quite that tall. Maybe somebody served in the military and got the GI Bill and then came back. And there's some 40 to 50, right? There's some that are older than that. There's some, I always wanted my degree, but I couldn't do it until my kids were fully grown, but now they're gone and I'm going to go back to school. You get some out here. There's not very many, but you find some that are significantly older. Right? I want to go back to school. I don't know if I ever will, but maybe at some point I will and study a little bit more. I'm already old. I'm already in my 40s. I'd be one of these people when I finally go back to school. The point is, most observations would be over here on the left, but you'd have this big long tail going out to the right. There's nobody who's 0 years old going to school. There's nobody over here. You can't be negative years old. I think that would be another right skewed example. Right skewed are fairly easy examples to come up with. Left skewed is a little bit harder to come up with. The best example I have for left skewed, it's kind of a morbid thing, but I'll talk about it. It's the age when people die, the lifespan of people in a developed nation, right? Fortunately, most people live a long, full, happy life. Like maybe this is, I don't know, 60 years old and this is 70 and 80. And, you know, a lot of people are living that long. It's awesome. Or even 90. Right? Maybe you got that grandpa that's 100 and it's really cool that he's still alive. You hear about on the news every once in a while someone who's 110. Right? Most people are over here between, I don't know, 70 and 90. But sadly, some people die younger. Right? Some people die in their 40s or 30s or 20s, or, I mean, it's really sad, but infant mortality is a thing. Right? You get babies that are dying. You get this tail going out to the left, sadly. Most of the data is over here on the right, but the tail is to the left. That'd be something that's left skewed. Symmetric bell shape. I haven't given an example of that yet. It turns out that symmetric bell shape is something that's probably the most important type that we're going to look at in this class. We're going to really study this normal distribution, so a specific distribution that's symmetric bell shape. And the reason why is because it shows up in a lot of places. It shows up in nature and in science and in math, and it ends up being really useful, this normal distribution. More on that in the next chapter. But for now, just trust me that this shows up a lot. Whatever you're looking at, I don't know, the height of fully grown redwood trees. Turns out that it has this shape. There's some kind of average height that a fully grown redwood tree would be. I don't know what the hell it is. And most trees are about that height, but some are taller, some are shorter. You're equally likely to be less than that average or more than that average. If you plotted the height of all fully grown redwood trees, it would look like this. And nothing special about fully grown redwood trees. Well, I guess redwood trees are kind of special, but that's not the point. This shows up all over the place. If you look at the size of cells in the human body, I mean, I don't know enough to speak intelligently about that, but if, I don't know, a red blood cell has a given size, but I bet you they vary a little bit, and sometimes red blood cells are a little bigger and a little bit smaller, and if you track data on a whole bunch of sizes of red blood cells, I can't even say it, I better be symmetric. Errors. If you have a 3D printer and you're trying to create something, it's not perfect. You want to create something that's 11 micrometers thick. I don't even know if that's a thing. Oh, your printer's trying its best, but it's going to be a tiny little bit off. Sometimes it'll make things a little bit too big, a little bit too small. The error made by computers and printers and that type of stuff is also symmetric bell shape. Symmetric bell shape ends up being really important. It shows up in a lot of different places, which is why I included it here. Those are some examples: symmetric bell shaped, right skewed, left skewed. Note I didn't give any examples of uniform. That's because I don't really care about uniform. I mean, something that would be uniform would be if you were rolling a 6-sided cube, a die, a bunch of times and tracking how many of each result you got. Say you rolled it 600 times. You'd expect about 100 ones, 100 twos, 100 threes, 100 fours, 100 fives, and 100 six. You might not get exactly that. Maybe you ended up with 98 ones and 103 twos or whatever. But it'd be roughly uniform. If you're making a histogram of your results, it would look like this. It wouldn't look like this, this, or this. There's some information on the shapes of these distributions. I think the key thing for now is to be able to identify them. And one more fact that I want to add is that outliers are significantly more likely if your distribution is skewed. So maybe I'll even write that. Outliers tend to come from these distributions, left and right skewed distributions. And maybe that kind of makes sense because you think about outliers as being observations that are significantly different, bigger or smaller than the rest of them. And when you have skewed distributions, those tails introduce exactly that idea. Why does that matter? Why do you care that outliers tend to come from skewed distributions? Well, one of the big use cases, at least in this class, for shape is for you to determine whether you're worried about outliers or not. So before you even calculate outliers or look at anything like that, what you want to do is figure out the shape. And once you know the shape, if it's right or left skewed, you're worried about outliers. If it's symmetric, you're not worried about outliers. Why does that matter? Well, because maybe you recall back in 1.6 part 1 that we had two different measures of center that we cared about, the mean and the median. And we had two different measures of spread that we cared about, the interquartile range and the standard deviation. And the big difference between mean and median and interquartile range and standard deviation is two of them were resistant to outliers. The interquartile range and the median are resistant to outliers. Right, that was a big important fact. Why that matters is what we'll see going forward is if your data is skewed, then you're worried about outliers. If you're worried about outliers, you want to use measures for center and spread that are resistant to outliers. Outliers tend to come from skewed distributions. So if shape, we'll call it, is skewed, the best measures of center and spread, maybe I'll just say, quote, the median and the IQR. Again, because if it's skewed, you're worried about outliers. If you're worried about outliers, use measures that are resistant to outliers. And maybe parenthetically, I'll add if shape is not skewed, is symmetric, which in our class is going to end up being the symmetric bell shape. If shape is symmetric, you'll use the mean and the standard deviation. So there's other reasons you care about shape, but I think one of the most common uses in this class for finding out shape is determining yes or no is it skewed, because you'll want to know what is the better measure of center and spread.